let's suppose that I'm asked to figure out if this limit exists or not. Um, it's like when you hit multivariable limits, things get really real. You either have to go down the rabbit hole of analysis, which is usually for math majors, or you need to just kind of sweep it under the rug and move on. You're kind of being faced with like a little bit of a combination of the two here. So I have this limit as this point in 3D space approaches the origin of this big old rational function. So what we're going to do is we're going to try a bunch of curves passing through 0, 0, 0, the easiest ones we can think of. We're just going to do a bunch of experiments. If we find two curves that give us two different answers, then we get to be done. We get to throw our hands in the air and say the limit does not exist, party, party, party. But if we keep getting the same answer over and over and over again, we start thinking that maybe exists. The problem is evidence is not proof, and just getting the same answer over and over again wouldn't be good enough for you to say what the limit is. And these limits are very hard to prove. In this case, I think the limit does not exist. So we need to make a whole bunch of choices of curves that pass through the origin. And here's some really obvious ones. You could set x equals 0 and y equals 0 and just let the z approach 0. And that's like coming into the origin at the z-axis. Similarly, you could set x equals 0 and z equals 0. You could set y equals 0 and z equals 0. So you're coming in from the three axes, okay? There's even fancier ones, like you could set y equal to x and then fix z equals to 0. And what that is here's 3D axes with x poking out at us, like poking out of the black screen. And then the y is pointing to the right and the z is pointing straight up. So they're like in the screen and the z is coming out at your face. So if x is equal to y, you can imagine this line that's like, it would be diagonal in the xy plane, which means it's kind of like coming out at your face, like off and to the right, okay? And also it goes back behind the screen, off and back and to the left. So that's the y equals x line that's in the yx plane, okay, and z equals 0. So we could approach that way. So you could get even fancier if you wanted to. Like, I don't even want to draw these, but you could fix y equals 2x and z equals 7x. That would be a curve that you could approach. You could fix y equals to x cubed and z equals to negative x. You could approach that way. So you could get really freaky with these curves if you think it'll help you get to the end of the problem, if you think it'll help you prove that a limit does not exist. But what I'm going to do is just work with these guys over here, these really simple guys. Usually these are the first ones that I always start with. Now, when x equals 0 and y equals 0, what you get is the limit as z approaches 0 of 0 over z to the fourth power. So up top, can you tell that when you substitute x equals 0 and y equals 0, all of these guys go away? And these two terms go away as well, so that's what you're left with. That limit is equal to 0. Similarly, when you substitute x equals 0 and z equals 0, everything up here dies, and down here you're left with y squared. That's 0 too. I can already tell that if I substitute y equals 0 and z equals 0, I'm going to get the same thing, so screw that guy, I'm not even going to do that. But what about this slightly fancier guy? What if x were equal to y and z were equal to 0? So what you get is the limit as x equals 0, as x approaches 0 of x times x, that's where the y, I substitute x for y here, so I have x squared. The z is 0, so these two terms die. On bottom here, I have x squared plus 0 to the fourth power. Well, that's interesting because this is equal to x squared over 2x squared. And so when you cancel out those x's and you take the limit, you're going to get 1/2. So actually, this limit does not exist, and these two lines of work, or the top line and the bottom line if you like, these two limits are the literal proof that the limit does not exist. Now, I want to compare that example to this other example. And as a spoiler, this limit does exist, and this limit is equal to 0. So you could compute some curves. You could choose some curves and compute the limit and see what you get. So if you were to fix x equals 0, you would get this kind of limit. The limit as y approaches 0 of 0 over y squared. If you set x equal to y, you would get 3 times x squared times x. You see how all the y's were substituted for x's here? Over x squared plus x squared. And that limit is equal to the limit of 3/2 x. Some of the x's cancel. That's 0. If you were to substitute m times x, so here, this is really cool. I'm doing infinitely many tests, right? I'm using any m I want. Y equals mx. That's infinitely many angles of approach. I get the limit as x approaches 0 of 3x squared mx, this was a y, over x squared plus mx squared. Bust out a little bit of algebra to simplify that guy. And what happens is 2 of the x's on top cancel with the x squared on bottom. And you get that that limit is equal to 0 as well. So I just did infinitely many experiments, and I got 0 every single time. Now, I could keep going. I could pick parabolas and stuff, but I am never going to do enough experiments for it to count as proof. It's always going to be evidence. Stronger and stronger evidence, never proof. So here's the thing. You may be wondering, like, well, what will I be asked to do? What can I do? So here's a cool trick. If f of x comma y were defined as 0, 0, you could use continuity theorems. This is a rational function, which means if it's defined, it's continuous. If it's continuous, the limit exists. So here's a really quick example. If it were the same function, but we were approaching 1, 2 instead of 0, 0, you're just going to substitute the 1 and the 2, and you're going to be done. You're going to be like the limit 6/5, boom, next problem. But the problem is you can't use that theorem here. But there are some math problems that you've been asked to do where that limit is going to exist because of those continuity theorems. It turns out that if you want to prove that this limit is equal to 0, you need epsilon delta proofs. Those are miserable. Those take a long time to learn, and usually we save it for a real analysis class. There is an example of an epsilon delta proof that you could read in Stewart if you like. But in general, I don't believe that your instructor will be requiring you to learn epsilon delta proofs for this course. So, to sum up, you can prove that the limit does exist using limit laws, continuity theorems, or epsilon delta proofs, but you probably won't be using those. You can prove that the limit does not exist by finding 2 examples that give you different answers, 2 different paths where the limits are different, and then you say that is a proof. And also, for the purpose of asking you math questions, you may be asked to guess what a limit is based on evidence. I just want to make clear to you that you may be answering math problems correctly by guessing, and that's totally cool and like mathematically legitimate. But there's a very strong difference there between saying, the answer looks like 0, and mathematically proving that it's 0.